Yeah, just waiting for the. Hi, everyone. We have a great webinar for you to discuss the advanced serial analysis with RIGOL's MSO8000 series oscilloscopes. My name is George Rivera, and I'm joined here with John Stancarone. We're engineers and sales managers for T Equipment. Joining us from RIGOL is Chris Armstrong. Thank you, Chris, for taking the time to join us. Are you there?
Thanks, George.
Chris is the Director of Product Marketing and Software Applications. He has almost 20 years of experience, 10 of which are with RIGOL in varying roles, and we're happy to have him here. Before turning over the presentation to Chris, and while we're waiting for any late joiners to sign up and get into the webinar, I had a couple slides about our company to show you. Also, just a housekeeping thing, we will send everyone copies of the recorded webinar and the slide deck afterwards. It might be a day or so before we get them out to you. And please do ask questions through the chat box, and we'll try to address them at the end of the webinar. So here briefly a little bit about our company. We're over 17 years old, and we're now a large stocking distributor. We really do take to heart the slogan, buy from people, not just the internet, and have a qualified staff here to help you. As you could see from the slide, as a national and international distributor, we cover the needs of a wide variety of customer types on the left side, and on the right side, you could see some of the product and instrument types we carry. In total, over more than 500,000 products. Our company has invested heavily in making the website a great resource. On the left side here, you could see some filtering capability by specifications to narrow your search. And on the right side is a screenshot of an internal portal that we have developed for better customer service when you call or email us. We're constantly enhancing our website and internal systems to provide you a better experience. And now it's time to turn over the presentation to Chris. Thank you again for joining us, and one moment here while I give you control.
Thanks, George. Let's see if we can't.
All right, there you go.
All right. So you can see that, George? All good. All right. So what we want to talk about today, thanks, George. Thanks, T Equipment, for putting this together. It's a great venue for connecting customers with, I think, technical, application-focused content that we hope you find interesting. And, of course, there'll be opportunities at the end here to ask questions and engage further for anyone who wants to talk more. But today what we're really going to talk about is advanced serial analysis and how you can use some modern tools to really get the most out of your debugging to be as efficient as possible when looking at a variety of these types of signals. And we're going to do that in a couple different ways. We're really talking about, kind of characterizing the signal integrity of your serial data. And depending upon your application and what specifically you're trying to do, that may manifest in a couple different ways, right? So we're going to start by looking at this data really in a true serial link, a connected link either on a board or wired in some way. And we're going to talk about how to capture that data using an oscilloscope and start to evaluate it. We're going to look at some advanced tools, first with the clock, making sure your clock's working correctly with the jitter analysis, and then looking at signal data integrity on the data lines with a couple different techniques, including some eye diagram analysis, where we look at timing, drift, issues like that, as well as amplitude noise, and then dive into some bandwidth and rise time and how that affects both the signal integrity in a couple different ways. And then at the end, we're going to talk about what happens when you try to put these same signals up on a carrier. I think common sort of IoT applications today, you have a transceiver set that's working on a serial link, but many of these signals end up needing to go up on a carrier for different RF applications. And we're going to look at ways to analyze the frequency up on the carrier to really demodulate. So we're going to be able to look at the data segment both in a wired sense and on a wireless sense, but with demodulation. And then look at some advanced data validation and bit error rate testing. So the goal here is to really familiarize you guys with tools that allow you to really do a complete debugging analysis of that encompasses board layout issues, crosstalk, noise, cabling issues that can really help you fully analyze and characterize in an efficient, cost-effective way all of these kind of serial signals that you're using today in modern IoT and electronics work. So one brief slide about the tools we're going to be using today and the tools I used here to make this presentation. Right? So we have our new set of oscilloscopes, the UltraVision 2 series oscilloscopes, have a great combination of memory depth and sample rate that make them really ideal for this kind of analysis work. We're going to look at time domain analysis, some frequency domain analysis, some serial decode as well. And then we're going to use the Jitter and I tools that are on the MSO8000 series. And we'll talk about that as we go through. So that set of oscilloscope technology, UltraVision 2, that really enables a lot of this analysis. Now, throughout this presentation, I use one of our new waveform generators that uses our Sci-Fi 2 technology. And we really use that for a variety of sort of signal emulation, modulation, and synchronization purposes in the DG2000 family. And then finally, when we're talking about signals on carrier, we'll look a little briefly at some of the VSA and ASK/FSK capabilities built into the real-time spectrum analyzer. And we'll talk about how the spectrum analyzer really is a great partner product for this kind of debugging because of the way it does its analysis. So let's start with just a quick data capture, getting started kind of mode with our signals. So we've got a clock and a data signal of varying quality that we need to identify further. So the first thing we do is we set up our scope to go ahead and analyze this, just triggering on the data channel here and looking at the data and the clock together. So obviously, when we first trigger on this, we get that sort of erratic data movement like we just saw in that clip, right? So hard to stabilize this signal right away. We'll talk about how to do that. But to kind of get this set up first, obviously we got to make sure we're probing these connections carefully and correctly, so we're getting the signals adequately and accurately displayed on the screen. At this level, we're worried about things like making sure our data and clock are appropriately synchronized. Looking at crosstalk and noise, other issues, start to identify those problems that we want to further debug. It can also be helpful here. We forced a pseudorandom bitstream sequence so that we have a known data sequence, and that's going to help us later as we follow that known data sequence really through an entire debugging set of tools. All right, so the next thing we want to do really is set up our decode. In this case, since we've got sort of one data line and one clock line, I use a fairly basic parallel bus setup to just with a one line bits. So that's all we're really doing. So we've got the associated clock channel. So we've set up the clock characteristics and thresholds and the data thresholds as well. Looked at the polarity, and we've set up the display and the event table within the decode bus so that we can show those decoded bits on the screen. So we're also able to use that event table to export data, and we'll show that in a minute. But the problem still is we still it's hard to capture a individual bit stream because of how we're triggering and where we decide to trigger that signal. So let's look at how we can trigger it more stably to really go to the next step in this debug process. So our goal really here is to trigger on a stable, not just from a signal and edge perspective, but on a bit perspective as well. So the edge triggering isn't well, the easiest isn't the right way to do it probably. There's a couple different ways we can set this up. Here we're using a duration trigger. So we've set a duration on the left, just off the left side of the screen, where there's a wide low bit. So we've captured the widest low sequence, and that allows us to synchronize so that, as you can see, we're always capturing the same set of bits in the parallel bus here. Another easy way to do this that uses some of the capabilities of the instrument is with a zone trigger mode. So here you can see on the bottom image, I've got the A zone and the B zone set up to not intersect, and so you're able to look at bit sequences that are non-intersecting and isolate a single sequence of bits to look at zoomed in or in a couple different ways. So lots of different ways to trigger depending on what your signal is, but there's handy toolkits including the zone trigger and duration for these kind of bit sequences. So obviously, if you're using a known serial link like I2C, SPI, RS-232, you can always trigger directly on that data sequence too. These instruments have a lot of advanced trigger capabilities for particular serial buses, but with this just single bit sequence, use the different toolkits like duration and zone triggering to really maximize your efficiency there. So now we're stably set up. We've got a stable trigger point, and we're set up to really capture the data we need. So now, how can we further evaluate it? Well, the first thing we can do now that we've got a stable sequence is we can use that decode mode and the event table to pull the data bits out. So here you can see it in the data table, and then we can export that to a CSV file, and we're going to save that for later analysis. So now we have that 100-bit sequence that on the screen there that we can use to really capture. So we know that's the data being shown on the serial device, and we'll use that later for comparison purposes. And as we said, the UltraVision 2 scopes here really are capable of some advanced decoding as well as triggering. So here on the decode side, these instruments can do things like parallel bus, RS-232, I2C, and SPI, as well as some automotive, LIN, CAN, FlexRay, and I2S and 1553B buses. So really a wide variety of serial buses that you can both directly trigger on and then decode just in the oscilloscope itself. All right, so now that we've figured out how to capture and really start to evaluate the signal, we've looked at areas where we want to debug a little bit further. And the first area where we want to go ahead and dig in and debug more is on the jitter, on the clock. So we want to characterize the clock, which in this case is the purple trace here in the middle of the screen, and look at changes in that. Now, of course, we've got a little measurement of the period here on the screen, but in simply a display mode, hard to capture changes in the frequency or the period of a clock signal because they're so minute, right? So when we're doing jitter analysis, we use a term we call a common term, time interval error. And what that means, what time measurements are, is TIE is looking at subtle changes in the period of a signal over time. So really, the period of those clock waves and how they shift from one to the other. Right? And that can help us understand both the timing of changes, what's driving the clock, any errors we might have in the PLL or other solution we have implemented to drive that clock signal. So let's see what that looks like. So one way to evaluate that, we would typically go out further. So we have 1,000 clock sequences or more on the display here. And so with all these clock transitions, we're able to then calculate long-term averages and deviations for the time interval error, cycle to cycle, and other of the clock measurements. But we can go further than that too, right? So here, what you see in the purple is what we call a jitter trend. So this is actually a tie trend, or looking at how the time interval error is changing over time. So you can see, even though we know this clock signal is a sort of a microsecond kind of clock, running at about a megahertz, we see subtle changes on the order of sort of hundreds of picoseconds happening as the frequencies shifting subtly. So you can see what this means is jitter trend. As the jitter trend goes up, it's towards the middle of the screen there. That's showing a positive change in the period, right? Which is a slower frequency. So subtle differences in how that frequency is being played, and that's really one of the advantages of the oversampling, the high sample rate, and the memory depth of an oscilloscope like this. Gives you enough of a data set to calculate those trends. Another way to look at jitter is with a jitter distribution histogram. So that's our pink little bell curve here in the middle, right? And this shows you how. So one thing is the purple trend is you're looking for changes over time, repeating trends, looking at issues and resets that indicate maybe where any issues are coming from. And then I like to use the jitter distribution, this histogram here, to look at other sort of non-random jitter that's being put into our clock. And really, this histogram here is a little bit. It's not quite a normal distribution. It's a little bit peaked in the center, indicating there's some sort of non-random activity here, and we could improve the clock a little bit further. So, using these jitter tools with the MSO, this is on the MSO8000 now. The jitter tools use that deep memory, and we have the result table, both the trend graph and the histogram. And using that analysis, we can make changes to maybe isolate our clock or improve the PLL circuit a little bit. And ultimately, we'd like to end up with a little more of a bell curve shaped distribution like this, indicating that the noise is a little more random, right? So, looking at how you're looking at the nature of your jitter, both in a time sequence with a trend and over longer periods of time with a histogram, are great ways to make sure that your clock signals are meeting specifications. Now that we've really isolated, now that we've improved the clock a little bit, now it's time to look more at our data signal. And really, the right way to look at a data signal is with an eye diagram. So the MSO8000 has this eye diagram analysis tool. So let's talk about for a minute what eye diagrams do and how they're made. Right? So really, this eye diagram you see here, of course, when we talk about the eye diagram, we're talking about the top half of that image there, where it's called an eye diagram because the center open space looks a little bit like an eye. Right? And what that is that's a series of thousands or tens of thousands of transitions of the signal as it goes from all the different types of bit transitions there can be, from 1 to 1, 0 to 1, 1 to 0, 0 to 0, and looking at them with sets of transitions on the display here. What we do is we capture that in long periods. Here we have, this uses 10 million points of memory that goes far off the screen on both sides. We capture those sequences, and then we use either the explicit clock, which is the purple signal here, or a recovered clock to pull those frames apart and overlay them. Right. So now we have a Keller density chart here that shows where all those crossings happen compared to where they should happen in time, and that really allows us to look for aberrant signals or signal fidelity issues, depending upon how what the specifications are that we need for these transitions. So an eye diagram is a great visual tool for evaluating these bit transitions and under different test conditions, how those bit transitions operate, and ultimately whether your signal quality is sufficient for your end application. All right, so what kind of issues can we see in an eye diagram? How do we identify different kinds of signal fidelity issues? Well, here's a couple quick ways I use to understand what's happening in an eye diagram. So, typically when we talk about kind of jitter or drift in the signal, now we've gotten rid of the jitter in the clock side, but in the signal side we also have some timing issues. Right? So jitter signal would typically shows how wide those transitions are apart, whether they're right on in terms of timing, or are moving around a little bit, and again whether or not that's sufficient for your needs. There's also a subtly different issue, which not just jitter or drift within the data signal, but its synchronization compared to the clock signal. Right. So obviously these signals need to stay synchronized, and so as the signal drifts in comparison to the clock, that can cause us issues as well. The blue rectangle there in the center shows you really the amplitude noise. That's the vertical noise on the signals. That's an easy way to see it, but obviously that noise is permeated throughout the whole signal, right? So it causes us issues in the transitions when noisy transitions, noisy bands on 0 peaks and 1 peaks as well. So this is a common cause of many issues for decoding or demodulating these ultimately the signal you're trying to capture. And then lastly, bandwidth, or rise time, which is really the easiest to see is rise time in that signal in the green rectangle. So the angle at which these transitions happen, and then how far they overshoot and undershoot is really a function of bandwidth and rise time of your signal. And optimizing that is an important characteristic of getting the signal fidelity to the point where you need it for your application. So let's look at each of these in sequence here. So as we can see, there's a little video sequence here starting. As we can see, this is a synchronization issue where we have, we're using the eye diagram to visually debug kind of timing and synchronization. And as you can see, where the data signal is shifting left versus the clock over time. And as we watch this, we'll see the eye diagram start to phase over and start to widen those centers. So this is this issue really is about making sure that our clock and data are staying synchronized. And so this is what an eye diagram looks like when that synchronization starts to fail. Right? So we've debugged the clock, and now we can debug the signal as well to really optimize versus that synchronization issue. Another way to look at this synchronization, or that really, actually, this is more just the frequency and drift in the data itself, is to look at the histogram. So you can see the white box there across the center of the eye is we're watching those transitions in time and how they pass through in time. So much like on jitter, where you can look at trends as well as the histogram to give you kind of a deeper data set. Here we can do the same thing, and we can look at hundreds of thousands of results on the histogram of how the timing on that transition happens. And this is a great indicator if there's systemic issues, non-random issues that are affecting your timing, your frequency transitions on the signal itself. So we use that to characterize any of the frequency noise or drift in the data itself, really not related to the clock. Okay, let that. So there's that video running where you have both the eye diagram updating and then you've got the histogram updating at the same time. And of course, the MSO8000 here has this capability to do both eye diagram results allows you to visually improve that data transmission sequence. And all the UltraVision 2 oscilloscopes have a histogram capability like this, where you could look at these transitions in a history on any of the UltraVision 2 scopes. All right, so we've talked about timing issues in the data. We've talked about synchronization issues between the data and the clock. Let's look at signal noise for a second. So common causes of this type of noise, and again, we're looking here at really the width of those the bits across the top and the bottom, and as they transition, that amplitude noise that appears on that signal. Important things to look out for when trying to improve the noise here, things like grounding issues. Also, we have board layout issues that could cause things like crosstalk. Might have power line noise that causes issues here. And as we work through that, we can improve the noise and start to see really the true signal come through as we are able to get rid of a lot of that amplitude noise. So here's a signal where we've got very little amplitude noise remaining, a pretty nominal, and with good timing and with good amplitude noise. But the crossing patterns here, still show possibly some issues with our signal bandwidth. So now let's move and try to optimize our signal bandwidth. So when we talk about rise time and bandwidth for these types of signals, how do we do that? How do we investigate it, and what does it really mean? Well, one way to just kind of simply characterize your signal rise time here we've brought the trigger onto the screen in this image, right? We've got we can see that rising edge, much easier to capture now that we've eliminated most of the noise, and we can use the precision measurement tool and the statistics here to really capture that rise time, which here is about 230 nanoseconds. Right? So we can improve that by looking at our device and tweaking some of the bandwidth to improve the signal speed, right? And we can get that signal speed down as in this system as far as about 8 nanoseconds with a much higher speed transition. But that might cause us other problems too. So when we're thinking about this, how is this rise time that we're fluctuating here as we change this this sort of diagonal transition to a more vertical transition? How is that connected to the bandwidth of the signal? It's really connected by pretty directly. So from the bandwidth, you can always infer the rise time. So rise time in a normal system is about 0.35 divided by the bandwidth. But there's complexities in thinking about how that will affect your signal. Especially when you've got an oscilloscope, you've got a probe, and you've got a signal. So the rise time of your measurement is actually a combination of the rise time of your scope and the rise time of your signal. And it's really best defined by this square root of the sum of the squares. So as an example, if you have a 500 megahertz signal going into a 500 megahertz scope, the square root of the sum of the squares tells you that actually looks like a 350 megahertz bandwidth or a sort of 989 picosecond sort of rise time, right? So you've got an effect here where if your scope isn't fast enough, isn't significantly faster than your signal, you'll get error on your rise time caused by the combination of the scope and the signal bandwidth. So what we advocate here is sort of is a 5x rule, which tells you that if your scope bandwidth is 5 times the bandwidth of the signal you're trying to measure the rise time on, your rise time error is limited to about 2%. So that's a good thing to keep in mind as you're looking at faster and faster signals with your oscilloscope. So another way, since we now know that rise time and bandwidth are interrelated, right? We can also use some of the different tools in this oscilloscope to look at the bandwidth and how really the bandwidth of this data signal, right? So here what we've done is we're using the Keller FFT capability in the bottom sort of third of the display there, and we're using that to capture the bandwidth of this slower signal, this initial signal we started with about 230, 240 nanoseconds of rise time. So we can see the bandwidth envelope over 20 megahertz or so. Then we can compare that to our faster signals. We improve the rise time, and we can see that that envelope, the purple line is the new line, the orange line is the original. So we can see that the more power and higher frequency components being displayed as we've increased that rise time. So you can see how both the rise time increases and how then the frequency envelope of that signal also increases. So a couple different ways to sort of debug and analyze those transitions. And of course, you have kind of multiple FFT capabilities on any of these UltraVision scopes. But we don't necessarily want that full bandwidth either, right? So we have to be careful. If the rise time is too fast, now we see this transition happening. We've got a much cleaner signal, but we see some overshoot there at the top and the bottom of those signals that could cause us some difficulties as well, right? So one thing we can do is we can we can use the eye diagram as a great visual tool to optimize really our eye shape and maximize the eye height, and by adding a little bit of rise time back here at about 30 or 40 nanoseconds of rise time, we think we've minimized overshoot, and we've got a great sort of eye diagram look. So we're getting really close now to an optimal signal that we think is going to be great for this particular application. So now that we've got our sort of wired serial link in really good shape, we feel like we've got some good signals. We've implemented also a little 2FSK modulation to put this simple bit stream up onto a carrier for wireless transmission to our device, whether it's a remote control car or a sensor node or something in the cloud, right? So we're able to use this 2FSK modulation, and now we're looking at this fast Fourier transform on the bottom half of the screen of the data signal we started with. Really, it has some noise and other capabilities on it. So when looking at that, this is now on the fourth channel. So we're using that blue channel that's the output of the 2FSK modulator, and we're doing the FFT of that. So an FFT, or a fast Fourier transform, takes that time domain data coming from the FSK modulator and puts it up on a carrier, or rather, transitions that to frequency space. So now we can see this Keller chart in the bottom here that's all about frequency space. So the center of the display for that Keller chart is 60 megahertz with a span of it's 50 without 10 megahertz. So left side of the screen is 55 megahertz and the right side of the screen is 65 megahertz. So we can see a little bit of the 2FSK motion there around plus or minus 1 megahertz, but it's pretty choppy, and that's really a result of the noise in the signal. So there's a couple different ways we can look at this. And once we did all our decoding, all our debugging and improvements that we did through the earlier slides there, using the eye diagram and the jitter tool. Now, looking at our clean signal, we can see, hey, we've got a nice 2FSK modulation happening coming off of that signal, much cleaner, and we can identify those two peaks really right at 59 and 61 megahertz. So we now know we've got that 2FSK modulator is working at about a 1 megahertz span and giving us a much cleaner signal for purpose of demodulating. And there we're able to use, so here we're using two FSTs together, one to show the Keller depth and one to show the peaks and the latest FFT. So all the UltraVision 2 oscilloscopes have that capability to do really all those things at once, which is a great tool for looking at RF carriers with an oscilloscope in an FFT mode. So the other thing then we can do is this is when we've pulled in our real-time spectrum analyzer to look a little deeper at the FSK analysis and characterize that modulation itself. So we've debugged our serial link, we're put it up on a carrier and with a modulator. Now we're looking at that output of that transmitter to see how that's working with as we debug our signals. So this is all about kind of considering how those signal fidelity issues in our serial data or in the underlying data, affect the constellation, the data integrity on the carrier. So the constellation diagram is the upper left part of this real-time spectrum analyzer display. Again, just has the two FSKs because we're in a 2FSK mode. We're looking at the two different bit patterns. You can see the red points huddled around the left and the right modulation points. You can see that real-time trace at the bottom left, which looks very similar to what we just saw in the FFT. We've got some error summary in the bottom right, shows us some characteristics of these signals. And then in the top right, interesting, the instrument's got the bit pattern that it's demodulating from that carrier. So we can look right at the bit pattern. So let's take a look at what this looked like when we had our kind of initial signal with our eye diagram. So when the eye diagram looked like it did on the left, the output of the carrier looked like this, right? So we see that familiar sort of awkward FSK in the bottom left in the spectrum itself. But as you can see in the top right, we have a lot of error, and we're getting some actual bit errors coming through, right? Some of the bits are moving around, even though we know that data sequence is repeating. Right, so some errors in demodulating this, really because of underlying errors in the serial link. So we're able to improve that. Now with our new improved signal, we have the eye diagram on the left, and now we can see with the output of the modulator into the real-time spectrum analyzer, we can see, hey, a much cleaner signal, a much cleaner spectrum. The constellation diagram looks solid, and we're getting really stable data sequences. So our kind of ability to debug this from a jitter, eye diagram, and ultimately in an RF sense have really cleaned up the signal and given us this pretty solid data throughput. Now we can verify that, lastly, by using a bit error rate test mode. So what we're able to do here is we took that data file that we started with, that we pulled off of the oscilloscope using the decoded bus bits. We pulled that bit pattern off. We've loaded it into the spectrum analyzer as known data. And now we're also you see the little yellow sequence of bits there is what we're triggering on in the spectrum analyzer. So it's a repeating set of bits that we're triggering on, and every time it triggers on that, it compares that 100-bit sequence to the 100 bits we loaded from the scope. So now we can tell for sure that we're getting no errors really at this point. So we've got the ability to say, hey, the data we were putting out of the transmitter, or putting it into the serial link originally, that we then improved and decoded. We're now getting that same data sequence every time coming through the modulation up on the carrier and being demodulated. So we've got really good data integrity throughout our entire system by being able to look at the debugging through this whole chain of events with decoding, jitter, eye diagram, up on carrier, frequency analysis, demodulation, and finally bit error rate. So the real-time spectrum analyzers include the new RSA3000E models, can do this type of demodulation with their ASK-FSK demodulation option. In the RSA5000 family, we have a full VSA option, which includes these and a bunch of IQ modulation formats as well for more complex signal types. And all of those both those instruments can do bit error rate calculations for their supported formats. So really great ways to set up and look at your data all the way through from a serial link to an RF carrier. So that's really what the decoding and the debugging we wanted to go through today for advanced serial analysis. If anyone's looking for more resources, we have a few really great resources available on the website, including our debugging app note for Jitter and I, which covers most of what a lot of what we talked about today. Our embedded design challenges talks about different types of errors in serial or parallel links as well. And then on the RF side, we've got you can always get the RF basics, which is a great toolkit for kind of getting into and understanding how these signals look in an RF sense. Was also the Basics of Scope video library, which has about 40 videos getting you set up and ready to go with how to use oscilloscopes, from triggering and decoding to other things. And then there's also a complex demodulation application page available to show you more about sort of the VSA and ASK/FSK capabilities. So that's really the end. There's my contact information if you need to talk to me. But for now, I'll pass it over to George, and we can go ahead and talk about any questions anyone has. George?
Hey, how are everyone? Please take a look at this slide here. It's got John's information. He's a better contact with more technical questions. There's a link at the bottom. We have a lot of other webinars that we've recorded, including one with RIGOL from last year. And if you visit that web page, you'll be able to take a look at those recorded webinars. While you're reviewing that slide, if you have questions, please use the chat box and ask the questions. There's already one question that we had from earlier that I've been saving for you, Chris. Both the oscilloscope and the real-time spectrum analyzer look like they can capture the signal on carrier. How do the two instruments compare for looking at RF signals below 2 gigahertz?
All right, so as we're looking at the 8000 series, so that was our oscilloscope, as we said, has up to a 2 gig bandwidth. So it has a 50 ohm front end, which is great for these typical 50 ohm signals, just like the real-time spectrum analyzer would have. The big difference is really all about sort of kind of memory depth and then what we would call sort of probability of intercept. So the scope does a great job of capturing deep memory and converting that into frequency space. What the real-time spectrum analyzer does better is it's able, because it's a real-time analyzer, it has a seamless capture mode where you're it's calculating the FFTs so quickly that you never miss any piece of the signal. So you're able to look at lower duration signals that either are short or don't happen as often, and find those in the RF signature, and you're able to then trigger on them in a frequency space using things like the frequency-based trigger or power trigger modes. So the real-time analyzer does a better job at capturing really dynamic signals and allows you to trigger on them in different ways. But an oscilloscope with enough bandwidth like the 8000 can do a great job of helping you visualize some basic RF signals like the ones we did there.
Thanks, Chris. Next question. When using the Jitter toolbox, what's better for debugging, the histogram or the TIE or TIE trend?
Yeah, so I think we talked about a little bit of this, right? I think there are different tools for different kinds of jitter. There's a lot of depending on the nature of the jitter in your signal, whether it's random or what timing kind of coefficients it repeats on, right? Will tell you a lot about sort of where it's coming from. So I like to use the trend diagram to find sort of your faster, how the jitter is moving over, let's say, 100 to sort of 5,000 or 10,000 transitions. But for things that are slower than that, like if you want to look at the jitter over 2 minutes or an hour, the histogram is a much better tool for kind of capturing longer term trends and then visually showing you kind of what the shape of that the overall distribution is, which tells you a little bit about the nature and maybe the cause of that jitter.
Okay, Chris, and just a reminder, you have opportunity to ask any questions in the webinar chat box. Here's one more question for you, Chris. How do you know if the signals you're capturing are going to be good enough for your final application?
Yeah, so that really, I think, comes to the heart of it, right? Whenever you're entering a design, right, you always have to have a plan, goals for your signal integrity, right? And that's a combination of your how you want to lay out the board. It's a combination of the environment you ultimately need to be using it, the data throughput you need, bandwidth. So all these things come together to you have to have a plan and a goal that gives you enough margin so that you don't end up having to refit boards or send them back out for another turn, right? And I think just being able to articulate what those goals are and then being able to test to them and leaving yourself enough margin is sort of the essence of a debugging in a design process. And so I guess I leave it to each engineer has a different way of kind of looking at those goals and those the signal integrity they need above and beyond the specifications. And really these are just visualization tools to help you kind of easily see what you're looking at and improve your signals to the appropriate standards, whatever those are.
Thanks, Chris. Looks like we're getting at the end of the time that we have allotted for you. And if anyone has any questions that they can think of later, feel free to give us a call or send us an email with them. We'll wrap up the chat. And as I mentioned earlier, we'll send everyone copies later today or tomorrow. You'll be seeing a recorded copy on YouTube for the webinar and a copy of the slide deck. Thank you so much, everyone, for attending. Thank you so much, Chris. I appreciate your time. It was well done. Good job.
Thanks, George. Thanks, everybody. Have a great day.
Bye. Bye.